Okay, so this talk is not a tutorial. It's the first non-tutorial talk in the workshop. It's more of an overview of challenges that we have when trying to do hardness of approximation for polynomial time problems. And I didn't realize this, but when making the talk, I saw there's so many challenges. So I'm only gonna cover some of them, and it'll be kind of quick. Like I'll talk about a lot of different things and spend not too much time on most of them. It's natural to get lost during the talk, but hopefully you'll get something. Some of the things will make sense, and you'll get some impressions. And you can have look at the slides later if you want to go back to things. Yeah, so let's start. Does this work? Okay. So yeah, so the plan is to give you like a quick overview to put things in context about like fine-grained complexity within P. So I'm gonna be quick here. So last year we had this week-long kind of crash course on this topic, and everything is online. So you can look into that. But I'll just like try to put things in context, and then jump into kind of hardness of approximation, and then we'll talk about a bunch of challenges. Yeah, so the context is, we have the class P, which has a lot of very nice problems. This is just a random subset that I like, where each problem here has some polynomial time solution, n squared, n cubed, and so on. And we'd like to know if we can do better. And for most of these things, we've been stuck for decades on each one, and so it's very hard to make progress on them. And we didn't before this fine-grained complexity literature in the last a couple of decades where we've been designing a lot of reductions between these problems. I guess we kind of didn't know which ones we should expect to solve, which ones are kind of really, really hard, and so on. And but now we can draw like nicer pictures that show more understanding. So we can put some kind of core problems that are conjectured to be hard on the top. And for each one, we can have like a class of problems that are hard under that core problem or conjecture. So, for example, there's this threesome problem. It's like a basic core problem that a lot of people have thought about for many, many years, and seems to be very, very hard to improve the existing algorithms for. But then there's like dozens of problems in its class, which are maybe less well studied, less famous. But the meaning of this class is that you cannot solve any of them faster until you solve threesome faster. So if a problem is there, then you shouldn't try to solve it. You should first try to solve threesome, and then you can maybe try to solve your problem. So besides threesome, there's other problems. There's SAT, which where if you assume the strong exponential time hypothesis that was mentioned yesterday, then you can get these quadratic lower bounds for a lot of problems, including the orthogonal vectors problem, which is like the canonical Seth-Hart problem that you reduce to, and then you reduce to a lot of other problems.
What do you mean by median?
Yeah. No, it's a graph median. It's a graph median. So you're going to compute the node that like the center of the graph, like that minimizes the distance to everybody else. It's not the array median. It's a graph. So these are just quick definitions of the core problems, and I don't really want to talk about them so much now. We'll mention them in more detail later. But the point is, these are like famous problems, very, very basic. Okay, so one of the non-core problems, but one of the problems that were in these classes. Again, there will be a lot of problems in the talk, and you don't have to remember most of them. But this is just one problem that I like to emphasize because it's like a very basic one, and that we will see when we talk about hardness of approximation. So LCS is a problem we'll mention. So longest common subsequence, the input is 2 strings of length n, and you want to compute the longest sequence that appears in both of them. And by appear, we mean as a subsequence. So you can skip letters, but it has to be in order. And so you're really trying to find a maximum matching between the 2 strings. So, but it has to be like a monotone matching. And yeah, so it's a classic problem that you see in undergraduate courses. You can solve in n² time with dynamic programming, and we don't really know how to do better, except for log factors. And this problem is closely related to the edit distance problem, which you might have heard about, where, again, you have two strings, and you want to transform one into the other by doing a minimum number of edit operations. Yeah. So it's a similar thing where you have quadratic simple dynamic programming, and we don't know how to do better. And yeah, and this, I like to mention these as like examples for why we might care about this very fine-grained understanding, if it's n² or n³ or linear. And this is like a slide that I always have. So there's this related problem that's similar to these edit distance type problems. That's slightly more complicated, where you have some kind of scoring function, and you try to find the two pieces of the strings that are most similar. And so it's called local alignment. And the point is that people really want to solve this problem on very large inputs, on DNA sequences. And so if you do the n² dynamic programming, it's too slow. And so what people use is this heuristic called BLAST, which is a heuristic algorithm that doesn't necessarily output the optimal answer based on the well-defined scoring function that you have. So it computes something, but it's fast. It's really linear time, and it has like a huge number of citations. So people really want to solve this problem, and so this kind of motivates these questions of trying to get these conditional lower bounds for n² and so on. And right, so because what we would really like to know is whether you can solve this problem fast in linear time, but also with guarantees, like let's say exactly, not with a heuristic. And since the early days of this kind of literature, we know that you cannot do this exactly. So if you want to solve this problem exactly with an optimal algorithm, you need quadratic time. So there's no truly subquadratic time algorithm under strong ETH. Is for all the three problems that I mentioned before. But it's very natural to ask, and it has been asked since the beginning, what about approximation? So what if you want a 1 plus epsilon approximation? So this problem is getting solved, so people really want to solve this problem, and they're using heuristics. So if we had a 1 plus epsilon approximation, we would be very, very happy. And yeah, so can we do that? And since the beginning, it has appeared very difficult to get such results. So such a hardness of approximation result is, we still don't know. And it will be in the next slides as a big open question in this field. OK, and just like a quick slide to put things in context. So within fine-grained complexity, there's multiple things that people are trying to do. One of them is this hardness of approximation thing, which is kind of like you take the existing lower bounds and try to make them kind of more useful, like maybe hold for approximations or for average case or for quantum and so on. There's like one kind of direction that people are looking at. And there's two other directions. Like one is just to try prove more and more lower bounds for like exact problems. And sometimes people have been finding algorithms as well, just trying to close the gaps. And the third one is like to investigate the conjectures themselves and the foundations of the theory. Where we ask questions like, why these conjectures, why three, and so on. I'm just pointing out that there's a lot of literature on this. And but the focus of this talk and the workshop is about hardness of approximation. OK, so what can we do? So we want to do hardness of approximation, right? So we have these classes, and we have these prompts in the bottom, and now we want to know not only are they hard to solve exactly, but also approximately. And in some cases, we can do this just by tweaking the reduction, kind of like when you show that three coloring is hard, you get a 3 versus 4 approximation factor. So the same kind of thing happens here too for some problems. And sometimes you can also just do like what Subhash mentioned yesterday, where you take something like graph products or something on top of a standard NP hardness reduction, and you get something. So there's things like that too. But in terms of general kind of gap amplification techniques, what we would kind of naturally try to do is the following. So we would take one of these conjectures x. We would define some kind of gap x, some gap version of that problem that is useful. So that if you take that problem and you do like the standard deductions or some versions of them, you get that a lot of these end problems are hard to approximate. So that would be the first step, like identifying such a problem. And then ideally, you would also do the second step, which is prove that the gap version is equivalent to the non-gap version. So you do this gap amplification for a conjecture. Okay. And so just this is kind of the framework that I guess I would have in mind when thinking about this. And I just want to make a couple of comments. So first comment is there could be multiple gap versions for a problem. So it could be that you will see a couple of versions later in the talk, but there may not be like one natural version, and that each one could like eat away at a subset of the class. Kind of. And the other thing is when you talk about these, so we have these three conjectures at least. There's actually others. And then should you expect like one gap amplification technique to work for everything? Like do you expect like threesum and gap threesum to be equivalent for the same reason that SAT and gap SAT are equivalent? So maybe and maybe not. So the point is, when you do these gap amplification techniques, it's natural to try to apply them to the other conjectures, but they will not necessarily apply. So it's kind of like it's less unified in the sense, in some sense, compared to NP hardness, where like there's the PCP theorem. It's like one theorem, and it kind of gives you everything. And similarly here, we have multiple conjectures. We don't have just one conjecture like P different from NP. And so, yeah, just want you to keep these things in mind. Okay, so that's the end of like the kind of the introductory part. Now let's see some open problems and some challenges towards them. And in some cases, I will also discuss some results. Okay, so the big problem that we started with and that received a lot of attention is getting this hardness of approximation for edit distance and LCS. So ideally, you would get, in terms of upper bounds, you'd get a 1 plus epsilon approximation. It actually, for edit distance, we didn't even have a constant approximation upper bound. There was only like polylogs. And then there was this BIS paper at Fox a few years ago where they got the first constant approximation. So there's still a big gap between this large constant and between the no lower bound that we have. Okay, so we would really like some lower bounds. And this is, I guess, these problems are canonical dynamic programming type problems. So this question is actually a more general, asking you if you have some dynamic programming solution and you want to solve it faster without kind of building the entire table. So you want to solve it approximately. How does that look like? Can you do this trade-off between accuracy and time? Okay, so there's two main challenges actually to this. So if you think about it, look at the reduction that we have for exact, which I'll show you in a couple of slides, then you'll notice two big challenges here towards getting this lower bound result. And we'll talk about both of them. So the first challenge is kind of like what you'd expect. That you'd need some kind of PCP because so these lower bounds are starting from SAT, and PCP tells you that SAT is hard to approximate, and that's kind of what you'd expect. But then the first thing that you say was, well, but the PCP theorem is, we don't have the best bounds. It's so non-fine grained. We don't, as was mentioned yesterday, we don't even know that ETH implies gap ETH, and so on. And even ETH is not useful for us when we're trying to do this quadratic lower bounds. So. Mm-hmm. Yeah, that's a good question. Like, is there even? So when we started looking at this question, there was not even a constant approximation, and there was a polylog that came after 10 papers going from polynomial to polylog. But then after 10 years of being stuck, there's this result that came out with a constant approximation. So in this common thing here, where you take this, you try lower bounds for a long time, but then it motivates the algorithms people to actually make progress. But here, it seems very clear that whatever there is won't go beyond 3. So 3 approximation seems to be a very serious limit. But at the same time, I don't have any kind of approach to get a lower bound, so I don't really know. So it's not clear. Yeah. Yeah, I mean, I wouldn't be like totally shocked if there was an upper bound, but yeah. So right, so I was saying, yeah, we need this PCP, but the PCP is not fine-grained, and what we would kind of need is an even more fine-grained, like a gap Seth kind of PCP, which I'm not going to define, but like you could define something like that, and it seems like you need to prove this connection, which we're very, very far from. And so there's another challenge that I'll talk about later, but let's just start with this PCP thing. And yeah, and some time ago, there was this framework introduced called distributed PCP, which you'll hear about later in a talk by Passin, which kind of essentially resolves this challenge. And it doesn't do this by proving this, so we don't know that Seth implies gap Seth, but it kind of does it for orthogonal vectors. So in the n-squared regime, we kind of have this kind of reduction from the exact to the gap thing with techniques that are related to PCPs. And so I guess then pictorially, you could say that we have identified this gap OV problem that implies lower bounds for a bunch of problems. Not for LCS and edit distance, that's still open. But for some other things, we have it. And so let me just quickly tell you what this OV and gap OV are, just to give you a sense. So OV is this problem where you get two lists of vectors, so n vectors and n vectors, and you want to find a pair that that is orthogonal. So if you look at them, there's no coordinate where they're both 1. So it's like this jointness. So you get n pairs of short vectors of dimension log n, and you want to solve this. This is a quadratic time problem. Seth implies that there's nothing subquadratic. And now a gap version of this is on the next slide. It's like, you look at the inner product and you want to approximate that. And so actually, the version that actually makes sense is maximization, not minimization. So it's max inner product. So again, you have the same setup, two lists of binary vectors that you should think of them as being very short. And it's like you want to approximate what is the best pair, which pair maximizes the inner product. And the gap version is like either there is a pair that has a very large inner product, or all pairs have very small inner product. And so what can you get for this? So like the exact version is essentially OV, and it was known to be Seth hard for a long time. And in terms of upper bound, there wasn't anything like even polylog or anything. It was n to the little of 1 was the best. And so there were no lower bounds without, with more kind of elementary techniques, we couldn't get any lower bounds better than 1 plus little of 1. And with distributed PCP, you can get something that's almost polynomial. Okay, and then it implies corollary very strong inapproximability for a bunch of problems, including LCS closest pair. So this is like, imagine if you had, instead of vectors, you had these strings, and you wanted to find the pair that maximizes the longest common subset, the LCS score. So there we do get very strong lower bounds, and you'll kind of see why in the next slide when I talk about the second challenge.
So you were saying that the best approximation best factor is almost polynomial? Is it like basically what you think that polynomial should be true, but you don't?
No. Actually, it's actually correct. I mean, there's a small gap between log to the 1 minus little of 1 is log over log or something, but the upper bound is also almost polynomial, so it's very, very close.
It's because that D is like this.
Yeah, D is. I mean, if D was larger, then you could actually solve it. So yeah, so I'm not going to talk more about this distributed PCP because Passin will talk about it, but I'll just quickly mention a couple of open questions related to this that Karthik will also elaborate on later. So one is, Seth to gap Seth. It's not even clear that we believe that this should be true, but I'm just pointing it out that we don't actually get this. We kind of get the consequences that you would get if you had this for NP, but not in the NP, not in the 2 to the n world. Another thing, this is kind of technical, so yeah. Sorry?
How will you define gaps?
You should look at Passin's thesis. It's defined there. It's It's like, yeah, I mean, in the natural way, you get like, it's like set exists, epsilon just for all delta something, but you also have some approximation.
The reason I said this because if you just cared about approximating the number of clauses, like, then you can do better than 2 power n.
Right, so it will be like for every epsilon there exists a delta and a k, such that k set cannot be 1 plus delta approximation into the 1 minus epsilon. They will be paired up.
Yeah, so the second thing is it's like a technical thing where we need to start from from set, and so when you start from set, you get hardness for OV on very small vectors like log n dimensions. But OV as itself, you could assume that it's hard even on like n to the epsilon length dimension, like polylog length dimensions. They're much longer, and so that's like a better conjecture as a starting point. And in fact, almost all lower bounds we have in P that are set lower bounds could be based on this OV on polylog n dimensions, and they would be stronger. But the only exception is the distributed PCP framework where we actually need the log n dimensions assumption. And so getting rid of it would be very nice. And finally, there are these variants of orthogonal vectors and SAT that have been introduced as kind of like secondary conjectures, like variants of conjectures that imply many lower bounds. And one of them is like, it's very similar. Like you have OV, but instead of asking, does there exist a pair, you ask, does there exist a vector that is not orthogonal to every vector on the other set? So it's just like a different quantification. Instead of exist, it's an exist for all. And you would hope that the same distributed PCP thing gives you that result, that exist for all is gap version is hard. But it doesn't for some annoying technical reasons. And this implies that many of the lower bounds that we have don't actually work yet for approximation. Okay, so that's like the end of this part. Now I'm going to move on to the next challenge, which now we think is like a much more serious challenge. I guess it was always clear that it's an even much more serious challenge in the context of LCS and edit distance. Okay, so like let's see how does the reduction from SAT or orthogonal vectors, how does it to LCS, how does it look like? So your input is like a SAT instance. So it's like some formula, let's say a CNF formula on n variables, and you're trying to reduce it to LCS. And the first thing you do is you split the variables into two, like the green half and the red half, and you enumerate all partial assignments to the green half and the assignments to the red half, and you try to find a pair that satisfies the formula. And you do this by encoding these assignments with gadgets on which you compute the LCS. So there's the green gadgets that correspond to the first half and the red gadgets that correspond to the second half. And you define the gadgets in a way such that the LCS tells you if the pair satisfies the formula. So the LCS is equal to some value x if, when you plug the assignments, you get a satisfying assignment. Otherwise, I get a smaller value. So you'd get a kx minus 1. And so, OK, so then that's like the inner construction. You're defining these small gadgets. But then you have all the 2 to the n over 2 assignments that generate all these 2 to the n over 2 green gadgets and all 2 to the n over 2 red gadgets. And you need to combine them somehow so that the final solution tells you whether there exists a pair. If you were just talking about this LCS pair problem that I mentioned before, then you don't need an outer construction. You just need this inner construction. You just say, I put this list of gadgets and list of gadgets, and I ask, is there a good pair? But actually, for like the real problem, we need some outer construction, which is some kind of careful way of combining the gadgets with some separator letters that I'm not going to go into. So you you write them in a long sequence in a special way, and this special way has the property that the optimal alignment will really depend on the existence of a good pair. So at the end of the day, LCS is like a matching between all these gadgets. So you have 2 to the n over 2 gadgets here, 2 to the n over 2. So you're going to match them. But the alignment will reveal whether one of the pairs was good. So this big N is 2 to the n over 2. And so when you look at the LCS of these two final strings, you're getting this big N times x minus 1. So this is the case where where all pairs were not satisfying. So for every pair you match, you get an x minus 1. But if there was a good pair, then you get the same thing plus 1. So this good pair will give you like an extra one score. And the problem is that this n is huge. It's 2 to the n over 2. It's like the gadgets are very short. Like in terms of if the whole thing was n, then the gadgets are like log n. So the gap is really like 1 over n kind of. And so this is why it's not a hardness of approximation. You would like to say, in the yes case, you get something, and in the no case, it's like constant fraction of that. Okay. And then, even if we had the PCP, it wouldn't work. And the reason is that a PCP, I mean, it's like telling you, it's like a PCP would say that SAT is hard to approximate. So like the formula in the yes case, it's like very satisfiable. Like all clauses, most clauses are satisfied, 99%. In the no case, like 1% of the clauses are not satisfied. So it only really affects like the gadget. So it really says, it could say that in the yes case, the LCS is something, and in the no, if the pair doesn't satisfy, it's a constant fraction less than that. And even let's take this to the extreme, and I suppose you have this magic gadgets that if the pair is satisfying, you'd have x. Otherwise, you would have the minimal value, which would be 1. Even then, the outer construction really hurts us. So then you would have maybe instead of n something versus that plus 1, you would have something versus that plus the length of a gadget, which it cannot be a subpolynomial. So the outer construction is really the issue. And maybe more kind of abstractly, the issue is that kind of what this reduction is doing is there's this implicit bipartite graph of kind of partial assignments, where you look at a pair of assignments and you put an edge if they would satisfy the formula. And so you have this implicit graph where you'd like to know if there's an edge. If there's an edge, then it's a satisfying assignment. And satisfiability is really deciding if there's an empty graph or if it has an edge. And when you do this, I mean, you get bad approximation factors. Okay. So then it's natural to say, oh, okay, but so now I'm trying to say, like, okay, let's try to fix this. Let's try to find some gap version that would give us this lower bound that we want, using this same reduction that we have, which is the only reduction we have for LCS. So then the natural thing is to say, well, okay, maybe I look at a bipartite graph and I ask you, is it a dense or sparse graph? And which in the SAT world would say, do most assignments satisfy the formula versus having no satisfying assignments? So if you actually had that kind of gap version, then yeah, that would be good, because then you do the same reduction, and then in the yes case, you would have many pairs that are satisfying. So then you would have to look at this gap SAT version, where you get a formula. In no case, there's no satisfying assignments. In the yes case, you have 99 of the assignments satisfy. So that's kind of the gap version you would like. Unfortunately, it's not a hard problem if you allow randomness, because then you can just sample an assignment and check, and that you would solve the problem in linear time. One thing what one could say is that, okay, but it's not so easy for deterministic algorithm. So if you had a deterministic algorithm, you wouldn't be able to distinguish these two cases. And so in some works, we actually went in this direction. And we introduced this framework for showing hardness for deterministic algorithms. And so we looked at these SAT versions. We had to look at not at CNF, but at formulas or circuits. It doesn't matter so much here. But then we use this connection between solving this problem deterministically and circuit lower bounds. So there's these connections that say if you solve this problem non-trivially fast with deterministic algorithm, then it gives you some breakthroughs in complexity theory. And then the bottom line was that we got the results we wanted for LCS and edit distance if the algorithm was deterministic, which is a big restriction because like we knew that randomized would completely break the instances that we're creating. But also, it's not really a hardness. It just says that if you did this, you would get some breakthrough in complexity. So it's not really a hardness result. It's just a barrier. OK, but let's go back to randomize. Let's leave this deterministic thing for now. So what can we do here? And the natural thing to say is, OK, instead of 0 versus 1, if I was only looking at a gap version where I either have a large matching or I don't have anything. So it's 0 versus a large matching, a linear size matching. So this seems like, yeah, it may be hard to solve. Because if you sample, I mean, you're not likely to hit a lot of the matching edges. But actually, what you would actually want for this reduction to go through is not just any matching. It has to be a monotone matching. I mean, so if the problem in the previous slide where the matching wasn't monotone, if you do the reduction, it gets messed up. And LCS can only pick monotone matchings. So you really get this question of 0 versus linear size monotone matching. And you could make some conjecture about this problem and so on. Is it hard? I don't know. But the first thing that one should do is to understand the query complexity of this question. So leave aside all this SAT and LCS and so on. You just have this query model where you have this bipartite graph, and you ask an oracle whether some pair is an edge, and you want to distinguish between the case of 0 versus a linear-sized monotone matching. So if we have hardness for this, it's likely to lead to some kind of lower bound for LCS. OK, so good. So that's like the end of those. So we already covered 2 challenges that were related to LCS and edge distance. Now we're going to talk about different problems and different challenges. And so the next challenge is going to be like gap 3-sum. So you could start maybe thinking, like, what would be a gap 3-sum version? OK, so we have this gap here. So what about the other classes? And so what's an interesting gap 3-sum? So I mean, multiple things have been proposed, but it's not clear that what is an interesting one. And I think an interesting one is the following. It's kind of related to triangles. So think for a second about triangles in graphs, which is morally similar to 3-sum. So this is a very nice gap version for triangle. So you get a graph, and you say either there's no triangle, or if there's a triangle, there's 100 clique. So it's like a gap clique version like we heard about yesterday. But here it's a much more fine-grained. So yesterday, Passin was showing that there's this 2, R and K, and you either don't have this or that. And we have very strong lower bounds there in the not so fine-grained setting. But in the fine-grained setting, we don't. So it's interesting to say how to push the limits of those techniques to this regime. Okay. So as far as I know, this problem could be linear time solvable. Or it could be as hard as triangle. And then now going back to 3-sum, I think this gives us a very nice versions. So it's not so easy to say exactly in 3-sum, but let me say 2 different versions. So one is when you look at in the plane. So 3-sum gives you this classical hardness to the question of you have points in the plane, and you ask, is there a line that goes through 3 points? And now a very nice gap version of this is, so either you don't have any 3 that go a line that goes through 3 points, or you have a line that goes through 100 points. So imagine you have points on the plane. It's hard to figure out if there's 3. But now I promise you that if there were, then there's this line that's really dense, that has 100 points. And that is very similar to this triangle versus clique problem. And this is actually a very well-motivated problem in like graphics and so on, where you have like these points, and there's this a basic thing they do is find these lines that go through points. And so for this problem, we don't know if it's linear or as hard as 3-sum. And then slightly more like additive combinatorics terms, you could ask, you get a sequence of numbers, and you ask, is there a 3-term arithmetic progression, which would be 3-sum? But here it's like either 3-term or 100-term. If there was a 100-term, it's like maybe easier to find because there's like more evidence to it. Yeah, so that's like, that's it for this challenge. It was a quick one, just raising these questions that I think are nice. And I think that the techniques we have that we heard about yesterday, the graph products and so on, I think they're very relevant to answering them. They just need to be optimized. And maybe, I mean, probably new ideas are required, but. OK, now I want to talk about another version of kind of triangle versus something version related to short cycles. So let me motivate that. But so in terms of the picture, so this will be about this class that is at the intersection of threesome and APSP. There's some problems that are here that are harder than both. One of them is this all-edge triangle problem. And we're going to look at a gap version of that. And then it's going to give us hardness of approximation for a bunch of problems that are related to shortest paths. So here's the motivating problem that we will try to show hardness for. Approximate shortest path. So you get a graph. Let's say it has m edges. So m is the parameter we care about. And we want to be really fast. We want to run in linear time. And then be able to answer distance queries. So it's like we process the graph. We create this distance oracle. And then we want to answer queries very fast, like in m to the little of 1. So the whole thing should be kind of linear time. And yeah, so how can we solve this problem? Solving this exactly, we know, and I'm going to show in a minute, like a reduction that shows that this is a hard problem. But then, OK, what is the best approximation factor that you can get? And yeah, so it's like this distance oracles, but you really care about the time and not the space. So when you hear about distance oracles, often people talk about the space complexity, and here we're talking about the time complexity. And the classic distance oracle that by Thorup-Zwick gives you this upper bound trade-off. So it says you can get this 2k minus 1 approximation in time that is m times this factor that depends on 1 over k, so n to the 1 over k. So the more you increase error you allow, you get faster and faster. And this is the classic upper bound for the trade-off. But in terms of lower bounds, what can you get? So I mean, that says that if you want to get linear time in that upper bound, you need k to be super constant. So you need k to be, when k is super constant, then this is almost linear. But in terms of lower bound, we only knew that the 2 approximation is hard. By simple reduction from triangle, which I'll show in a minute. So here's the reduction. So this will also motivate this short cycle thing that I want to talk about. So we show the reduction. The parameters don't really matter, but if you want, they're there. You can just think of it kind of pictorially. So you have a graph, and you want to detect if it has a triangle. And the graph has n nodes, n to the 1.5 edges. And let's assume you need quadratic time. So this is the upper bound that we can get is quadratic for this problem. Let's assume you cannot do better. So how do you use a distance oracle to solve this problem? You take the graph, you delete the edges between B and C, between these two parts. And you get a new graph. And then you run your distance oracle on this new graph. And then you make queries. So for every pair BC that used to be an edge, you ask what is the distance in the new graph. And the point is that if the pair was in a triangle, there's a 2 path. So the distance is 2. But if the pair wasn't in a triangle, then there's no 2 paths, and the distance is larger. So it's at least 3. And I mean, if you compute all the parameters and so on, if you had a very fast distance oracle, then you would solve the triangle problem in linear time, n to 1.5 time, which we believe is not possible. In fact, you would refute threesome, but I'm not going to go into that. OK, so but in terms of the approximation factor that we got here, so 2 versus 3 is hard. So better than 1.5 approximation is hard. But actually, because this graph is bipartite, then if there's no triangle, the distance would be 4. So you have to like zigzag, and you'd get a 4. So this is actually the 2 lower bound that I mentioned. Okay. And can you do better? So you would hope to say that, well, yeah, like, if in the no case, the distance needs to be very large. But actually, you can already see that if this pair was in a cycle in the original graph, like this 5 cycle, then the distance would actually be 4. So kind of like, the existence of these short cycles is really what's making the gap bad. So there was this lower bound, and so we want to get much higher lower bounds, and then it's really about this gap version where you look at the cycles. So here's a gap triangle version that would give you a very good hardness of approximation for the problem. In the yes case, there's a triangle. In the no case, there is no short cycle. So there's no cycle of length less than 100 in the graph. And it's open, and it's actually still open if this problem is easy or hard. So is it easy in the sense of linear time, or is it hard that it requires some super linear time for it? What we could actually prove is that triangle is hard if there's few short cycles. So it's like we cannot eliminate all cycles, but we can eliminate most of them. And that gives us many applications, including the distance oracle lower bounds. So for distance oracles, we did get a lower bound that almost matches this. The constant in the O is not tight, but essentially this trade-off of Thorpe and Zwick is the right one. So you cannot get if you want a constant approximation, you cannot get linear time. And so in a follow-up work by Say and Jinjan here and us, so we have this new way to do this cycle removal with additive combinatorics. So I'm going to mention that too. But then we get even better bounds. So the trade-off, the constant is just a factor of 2 away. OK, so let me quickly mention these techniques. And the reason is that it's reminiscent of some of the things we heard about yesterday, but not quite. So I think it'll be interesting to look at. OK, so let me tell you how we prove this statement. So we prove that triangle is hard even when the graph has few 4 cycles. So we prove it for short cycles, but I'm just going to focus on 4 cycles. You get the ideas. And the exact parameters, I'm going to go quickly, so don't really worry about them. You can go back to the slides and see them. But this is kind of the picture that I want to highlight. So there's like 2 steps to this reduction. We take a graph. So there's going to be a reduction from triangle detection to triangle detection with few cycles. So we take a graph. It's a worst-case graph. It has a lot of cycles. And we do these 2 steps, so dense piece removal and subsampling. And at the end of the day, you get the graph with few cycles. And the subsampling is similar to what we saw yesterday. So you get a graph and you subsample it. And this kind of makes sense in our context because when you subsample, you're eliminating the 4 cycles faster than you're eliminating the triangles because they have more nodes, so it's easier to hit them. OK, so this is kind of like the approach that we're trying to take. But unfortunately, when you do this starting from a worst-case graph and you compute the parameters, you don't get the result you want. There's just too many 4 cycles. And that calculation is important. So in a worst-case graph with that density, the number of 4 cycles is 2.5, enter the 2.5. But in a random graph, with the number of 4 cycles is only n squared. And so the point is, if you had a random graph and you do this subsampling, then you would get the result you want. Then the number of 4 cycles that you end up with is actually good enough. And so Bastian mentioned this yesterday, that there's this hardness of approximation result that start from random sat. So if random sat was hard, then you can get things easily. And this is kind of like what would happen here. If you had a random graph, then you would get the result. Unfortunately, random triangle detection in random graphs is not a hard problem. So it's not really that. But the thing is here is we only want the graph to be random in the sense of having few 4 cycles. So it's like pseudo-random. And then this first step, which is the main step, is that we can actually get to this setting. So we can go from worst-case graph to the pseudo-random graph by a process that we call dense piece removal. The idea is that if there's a subgraph that has a lot of 4 cycles, then it's denser than you'd expect. And so you go and you remove that part from the graph. And after you do this process, you get a pseudo-random graph. So that's what I want to say for that. And just quickly to tell you how additive combinatorics comes in. So when we did this, I mean, with the 4 cycle, we could do this, but the bounds were not as good. we still had more force cycles than in the random case, so it wasn't completely pseudo-random. But then when we looked at like this worst case graph, and you said, okay, wait a minute, so we're talking about this problem that's three-sum hard, so it means that you can start from three-sum and you go to this problem. So when you go to the worst case three-sums, maybe when you do the reduction, you don't have this worst case number of force cycles. That's not true, because when you look at this, then there's this structures in the three-sum instance that generate force cycles. These are Sidon sets. But then we said, okay, maybe we can do this dense piece removal in three-sum. And that actually worked and gave much better parameters. So you start with three-sum, and you identify these kind of additive structures, and you remove them. And then you do the reduction to graphs, and you get a graph that's pseudo-random. So that's the end of this challenge, and I just want to highlight that it's still open whether we can completely remove all the cycles to get like 0 force cycles or 0 k cycles left. Good. Okay, so we just have 2 more challenges that will be very, very quick, and then. Okay, so the next challenge is going to be about another problem, dynamic matching, and we're going to look at a gap version of OMV, which actually is still related to triangles. I'm not going to say it in the language of triangles, but I could have. And so this would be like a third triangle version that one could look at and show hardness for. So the motivating question is this big open question that it was also there from the beginning, and one of the most kind of famous open questions is for dynamic matching. So you have a graph and it's dynamic, it has additions and deletions, and you want to maintain the size of the maximum matching in the graph, and you want to approximate. So we know that this problem is hard, and in terms of approximation algorithm, there's been so much work on this. I mean, maybe 100 papers in the last decade or so, including these best papers by Tachafol and others, where they got a better than 2 approximation. So this is in terms of upper bounds, you can get a better than 2 approximation in this polylog time for updates. So the update time is like this, it's like the gold standard to get the update time to be polylog. And so like answering this open question positively would be like the next best thing to an exact algorithm. And in terms of lower bounds, so actually only recently, Yang Liu suggested this gap version that would actually solve this problem. So he showed that this problem is actually equivalent to understanding this gap version of OMV. So what is OMV? OMV is online matrix vector multiplication. So it's like Boolean matrix multiplication, but one of the matrices is coming online. So you have this fixed matrix A, and then you get these VIs, one after the other. And when you get the ith vector, you need to compute its product with the matrix. So these are n by n matrices. You get a sequence of n vectors. Every time you get a vector, you could have computed it naively in n squared time. So the conjecture is that you need n cubed time for this process. And gap OMV just says that you can have errors. So you have to compute this product, but the vector that you output could have an epsilon fraction of errors. Okay. And this turns out to be equivalent to the dynamic matching problem. And it's a very interesting open question to prove that OMV reduces to gap OMV. And this is a problem that, I don't know if it's super hard or not. It could be within reach of current techniques. But the result would be very nice, very satisfying. Okay, now I'm going to end with a problem of like a very different flavor. It's like a very open-ended problem. So it's a challenge for you. Can you find a natural NP-hard problem that you can compute in polynomial time? You can get an alpha approximation. But if you want this running time to be much faster, then you need to suffer in the approximation factor. So if you look at the, this alpha approximation, maybe it's some n cubed or n to the 10 or something. And if you want to go below that, let's say to get to linear time, then you cannot maintain that alpha. You have to, the approximation factor needs to be worse. So, yeah, I'm sure there are problems like that, right? Because when you have more time, you can probably approximate things better. I don't know if, we cannot prove it, that this is the case for any natural NP-hard problem. There are many candidates, actually. Here's just one that I know, then there's others. So Steiner tree has, it's a candidate in the sense that it's probably like that, but we don't know how to prove that it's like that. So we know that in linear time, you get a 2 approximation. And if you allow a larger polynomial time, then you can get this 1.3 something. And in terms of hardness, so we know that it's NP-hard to get 1.01. So to show that this problem is, like, to resolve the challenge with this problem, what you have to do is give me a fine-grained lower bound, under Seth or under threesome, or it doesn't matter, some kind of conditional lower bound with an approximation factor that's higher than this 1.3. So if you show that 1.4 is hard to do in subquadratic time, then you would show that, if you give me more than quadratic time, then I can get better approximation factors. And in fact, we don't even know how to show anything higher than the 1.01. Which would, if you showed like 1.02, you wouldn't resolve my challenge, but it would be nice. You would show that, Seth and these fine-grained assumptions can help you prove hardness of approximation results for NP-hard problems. Yeah. So maybe Kartik will talk more about it later. And I think it's related to the thing that these approximation algorithms, they often involve some linear programs. And those can be solved fast usually, but still, a lot of the time, for example, for Steiner tree, it's true that you solve a linear program in the end, but the linear program size seems to be inherently superlinear. Like you go over triples of nodes in the graph and you do something. So it seems like you need at least cubic time. But we don't have we don't have ideas for showing these results in terms of lower bounds. Okay, that's the end. Thank you for listening.
Any questions on top of these questions?
So in the slides when you mentioned size n method matching, if you do random sampling, would you actually solve that in time? What is your time?
Let's see. If you sample, I don't think so, right? Like you need to sample n times to catch one of them.
N edges
N edges.
out of n square choice.
Yeah.
So just think if you sample n times.
What about the non-monotone? Then how much do you need then? Like to get a maybe not 0 versus omega n, but let's say 1% versus 99%. Right? It should be.
I think more about this.
Yeah. I think monotone should be, as far as we know, it's not easier than the monotone, than the non-monotone. But of course, proving it is going to be harder.
Let's thank Amir again.